I'll be working off of that, but the dinosaurs, so I love them anyway. Nonetheless, before there ever was a geological column that had firm dates on it, of millions of years or things like that, the geological column was assembled in primarily the early 1800s. It started a bit before that in the 1700s. The late 1700s through early 1800s, people started realizing that there were relationships to the sedimentary rocks and the layers and the fossils that were. And eventually people started to recognize, especially through the work of William Smith in the early 1800s, that different types of fossils were found in different layers of rocks, and you could use the fossils to consistently orient yourself when you went to a new place where nobody had looked at those rocks before, and that the fossils could actually be used as markers vertically through this column of rock. And this became known as the principle of biological succession. This was all worked out prior to Darwin. So we're not talking about Darwin inventing the column in order to create a theory of evolution. What happens is that Darwin is taught that there is a geological column as a student when he was still a creationist of sorts. When he was an old Earth creationist, he was taught old Earth geology in the early 1800s by Adam Sedgwick, who happened to be the very first professor of geology in the history of the world. Pretty cool. And also pretty recent, because Sedgwick became a professor of geology in the 18-teens, I think that it was, 1820s. And so geology professors are pretty recent. We've had biology professors for a lot longer because we have bodies that need to be fixed, and we needed medical people and things like that. And of course, we had astronomers and physics people before that. Geology is a little bit later on as a discipline, as things go. We've always been interested in rocks, but we were always interested in rocks about what they were and how we could use them to build stuff. The idea that the rocks could actually tell us something about Earth history was a newer development that really started to make its way in the 1800s. So in the 1820s, 1830s, 1840s, we see British and French and German geologists primarily working out this system to understand that you could use these rocks and their orientation and figure out layerings and thus start to build this vertical column of rock. And oh good, I have a pointer over here that I can use. So there were no numerical dates because nobody knew how old anything was for certain. It was being used mostly on the basis, or was being built on the basis of fossils and also the positions of rocks with respect to one another. I'll give some examples of that. The radiometric dating came much later, more than a century after that. Radiometric dating was theorized first in the 1930s and then applied really in the 40s, 50s, and onward with the discovery of radioactive elements, which only really happened in the early 1900s. Sorry. So you get carbon dating, which was proposed and first implemented in the 1950s. Uranium dating was introduced in the 1950s as well. So these dates came around a lot later. The column was established prior to evolution and prior to numerical, what are thought to be robust mathematical determinations of the age of the Earth. Now, many of the geologists who were putting together the column did think that the Earth starting to talk in terms of hundreds of thousands and even millions of years. Billions wasn't coming on the scene just yet, but they were thinking it's quite a ways. In fact, Charles Lyell had estimated that the Cretaceous period ended 70 million years ago. And conventional geological dating would say it's 66. And so if you're a geologist today, you're looking at Lyell and saying, my goodness, that's pretty impressive for having no mathematical basis for this aside from looking at sedimentation rates and naively thinking maybe those could give us the number. So you end up with something like this, the geological column, which again is on the back if you'd like to grab one. So on the left-hand side, we have the conventional dates that are provided by regular geology. Oh, sorry, I tend to move around. I don't want to step out of frame for the folks watching online. And on the right-hand side, what we have is a proposal for how to understand these same rocks from a young Earth creation perspective, dividing the Earth's history into 3 geological periods, if you will, or three geological zones. Those rocks that were formed during the creation week, those rocks that were formed during Noah's flood, and those rocks that were formed after Noah's flood. Now, this is a proposal. It is not a hard and fast sort of thing that I can tell you with certainty that I know exactly where the divisions are in this. This is an area of active discussion and, quite frankly, rancorous debate within young Earth creations. And we got a lot of people passionately advocating their own position. I passionately advocate mine, and other people think that I need to go take a soak and think about different things. That's fine, but it's my talk, so I'm right. But how we get to these decisions about where the beginning of the flood may be and where the end of the flood may be, those are a talk for a different time. But at least for right now, one of the things that I can say is that all young Earth creations are going to be actually about placing human fossils in the post-flood period, even if they think the end of the flood is higher into the yellow unit here, the Cenozoic, than I do. All of us are pretty much of the same opinion that no matter where the flood ends, the human fossil record starts after that. And we'll see why. But I want to introduce you to dead white guy number 1. This is Nico Steno, also known as, actually his birth name was Niels Stenson. He went by Nico Steno, or when he was writing in Latin, Nicholas Stenovus. So he wasn't constantly running from the law and changing his name. He was just adapting his given name to whatever country he happened to be living in. He was born in Copenhagen, in Denmark, and wanted to be a surgeon. He wanted to be a medical doctor, went to school to study biology. This was during the religious wars period of Europe, and he died of starvation as Copenhagen was under siege at the time. Nonetheless, he survived, and he eventually made his way to Italy. He went to France first, worked for another biologist, another anatomist, who did not treat him well and stole some of his work, but eventually Steno was able to reclaim that because he was well known for his delicate skill with a scalpel. His father was a watchmaker and a clockmaker, and it turned out that attention to detail served Steno very well because he was apparently very, very careful in his work. And he eventually got hired to work at the first ever scientific think tank established by the students of Galileo in Italy and funded by the Medici family, which has a long and interesting history in the history of science. And as he was there, he got interested in the question of what fossils were. This is the middle 1500s. He's living in, let's see, middle 1600s. He's living around 1640, 1650 at this time. And there's a question about what fossils are. Two camps. One believes that fossils are biological remnants of organisms that somehow got into rocks. And another group thinks that they are geological phenomena that simply look something like biological things. Because at this point, nobody's got a full skeleton of a dinosaur or anything like that. They have occasional bits of shell and teeth and things like that nobody's really certain exactly what they are. And in fact, if you talk to somebody at that time about what we now think of as shark's teeth, they called them glossoptera, which meant tongue stones because they looked like little tongues. And they weren't sure if they were minerals or if they were fossils. They were biological. He had seen enough biology to look at these things in the fossil record and go, that's from a living thing. But I have to figure out something. I have to answer a hard question that's from the opposite side, and that is, how do I get a solid object inside another solid object? That's a very good question, and nobody knew the answer. And so Steno decided that in order to answer that question, he needed to figure out what these things called rocks really were like. And he started to recognize that the rocks around Italy, where he was, if you went to the foothills of the Alps and was looking around, you had sedimentary rocks that were tilted like this. They're sandstones and they're limestones and there's quarrymen working and things like that, but these rocks are tilted at angles. And he's like, when I go to the beach and when I go get fish so that I could do a dissection for my students and things like that, the sand is just this big flat horizontal sheet. And yet I see sand in the rock and it's tilted. that's weird. How did that happen? So he started understanding a couple of basic rules of geology. He wrote about these in a 70-page paper that he promised was just the beginning of a much larger dissertation on the topic of geology. 70-page introduction. Called it Podromos. He sent it through, he converted from Lutheranism to Catholicism, I guess when in Rome, or when in Gubbio and Naples and whatnot, wherever he was hanging around. He eventually converted to Catholicism. So when he wrote, he passed his book on to the Catholic Censor Board for them to look at. That was, kind of their publishing group and see, does this comport with Catholic theology? It sailed on through. And he wrote from a distinctly young Earth creation perspective about this. It's one of the things that I like going back and looking at with Steno here. The basic rules that he understood was this idea that we now call original horizontality, of the concept that sedimentary units originally began as flat-lying materials. When he went to the beach and he saw that sand, he went, this is flat. So when I look at a rock and it's tilted, something had to happen to make that sand go on end, because sand doesn't do this. Sand just spreads out. So that's really interesting. And then the light dawned on him that if I have flat things and I have stacks of flat things, then the things that are on the bottom must be there before the things above them come about. Now, this is still before Newton writes Principia. This is before an understanding of how gravity works is out there, but we still know that things fall down. They are still working in an Aristotelian physics and whatnot, but nonetheless, things fall down. And if you were to come visit my home and take a look at my desk, you would find that it's quite a mess. I'm not a neat person when it comes to my organizational system. And so if you asked me, hey, did you read that paper that I sent you? And I said, yes, I did. When was that? That was 3 months ago. Okay, I'm going to start digging down through my pile. Because it's older. And the things that I have looked at more recently are piled, sadly, on top of the paper that you sent me, and I did read quickly, briefly, whatever it was. But I've got to find it down through the stack. Steno figured out that that's the way rocks work, too. Sedimentary rocks that are stacked have the older rocks at the bottom and the younger rocks towards the top. And one of the things that he also figured out, a third important one, is the law of what we now call, or the rule of cross-cutting relationships. And that is that if you've got a rock and something else is cutting through it, whether it's a fault line or a tube of lava or something like that, then the thing that's cutting through the rock has got to be younger than the rock that it cuts through, because you can't have something cut through nothing. I tell my students, like, if you have a loaf of bread, you can make a slice. But if you don't have a loaf of bread and you have a knife, we need to come and take it away from you. Okay, this is not good behavior. Right? Don't tell me it's practice. Practice for what? Get a loaf of bread, right? So you can only have a slice after you have a loaf. In the same way in geology, you can only have something affect a rock if the rock is there. And we hear that and we go, well, that makes a lot of sense. And everybody else heard that and said, that makes a lot of sense, but it takes a smart mind to figure this out the first time, when nobody else had done that. Now, Steno is doing all of this so that eventually he can come to the answer to how it is that a solid is solid there. He eventually becomes a priest. He takes on a vow of priesthood. He continues to dabble and teach in biology, but never returns to geology, and sadly died at the age of 42, mostly because he treated himself very, very poorly. He took on a very acidic type of lifestyle. I think that Steno could never quite come to grips with the grace that God had given him. He accepted it. He knew that God had saved him. He was a passionate Christian, and yet I don't think he ever felt worthy of that grace, which is true, we're not, but I don't think that he ever could quite internalize it and value himself the way that God valued him. And so we lost a brilliant mind early. So a couple of these, going the wrong way here. There we go. So as I've said, old rocks are on the bottom, young rocks are on the top. So now Steno can go to a rock outcrop and he can start seeing something that nobody has ever seen before, and that is a story. the rocks were not just made this way by God at the beginning. They have a history to them. They tell a story. They record history inside them. And now Steno has opened up the Rosetta Stone for us to read the rock record for the very first time. And almost nobody read his stuff. Because everybody in England and most of the people in Germany are Protestants and aren't really caring at this point what the Catholics write. And the only reason that Steno becomes better known in England is because somebody plagiarized him so badly that another of the geologists in there said, "This guy isn't that smart. I know him. This came from somewhere. I swear it." And he tracked it down and found that he had plagiarized almost all of Steno's work. And it's like, this was the guy. It was the Dane. It wasn't you, you moron. Your sins will find you out. I don't remember the name of the guy who plagiarized, but I remember Steno. Here's an example of those cross-cutting relations. You have a fault between these sediments, and it offsets them, and you can see this white, oops, sorry, not used to this clicker, but that white line should continue across, but it doesn't. It's got this fault. So the fault's got to be there after all the sediments are around. And then notice what happens. The fault kind of dies off over here, and this unit is contiguous. So that must have happened after the fault. Now, I haven't told you how old this rock is, but what I can tell you is that this stuff is older than the cut, and the cut is older than that. This is the youngest thing. It's a relative dating system, not an absolute one. But it's still absolutely right. We've found a rule of logic that we can apply to the fossil record, to the geologic record. And so when we go to places like the Grand Canyon, and I hope you get a chance to do so, it's a phenomenal place, you will see a whole bunch of these layered sedimentary rocks sitting on top of some granites and metamorphic basement rocks of the continent. The stuff is draped on top of that, and then we can follow these rocks, and they're in these kind of stacked relationships. And the further you go north into Utah, you get into higher and higher rocks, but people have drilled for oil down there, so we know what the rocks are deep down below. There's the same ones in the canyon. So it's not like they're all stacked like dominoes that stop here and stop here and stop here. No, they're continuous all the way through, and we have a mile's worth of rock above you when you're in the Grand Canyon. And then as you get out of the Grand Canyon, by the time you get all the way up to Bryce, there's another mile. There's 10 miles worth of rock here. Vertical miles. That's a lot. Whew. What can do that? So Steno never got to the answer of paleontology. He came awful close. It would be James Hutton who would actually articulate this idea through his rule of inclusions. The rule of inclusions tells us that if you find a rock inside some other rock, then the rock that's inside had to be around first, had to exist first, right? You've got to have this pebble coming from somewhere in order to put it into this other rock. And that would end up being the answer for the fossils as well. The fossils get incorporated into a loose group of sediments before they're rock. You don't have to put a solid into a solid. No matter how hard I press the cat, I can't get him into the, like, don't do that, right? The cat gets very angry. You end up with a lot of stresses. You push, a little joke goes off later on, but it's still dubious. You can't take a solid object and crush it into another solid object. You don't get fossils that way. But as Steno figured out, sedimentary rocks weren't created in place for the most part. They are residues of erosion that happened either during creation week, as God, say, raises the continents out of the waters. We get some sedimentary rocks during creation week. Or during the flood, where we have large amounts of sedimentary activity that happen. And Steno actually put the first system together for understanding the rocks of any one place, where he lived around Tuscany, Italy, and said, these are the rocks that I think were formed during creation. Then some of them were dissolved. We would now use the term eroded. They didn't quite have that concept yet, but he believed some of them were dissolved and then collapsed during Noah's flood, and more things were made during Noah's flood, and then at the end of the flood, more things were dissolved, and after the flood, more things happened. So he actually divided the geology of Tuscany into pre-flood, flood, and post-flood rocks. It's really impressive. Two paleontologists working in different places might find the same fossils in different sorts of rocks. So here we have a paleontologist on the right who's working on a limestone, the gray kind of boxy thing. You all are living here in Missouri, lots of limestone. Everywhere you go, limestone all over the place. I like limestone because limestone has things in it that interest me, fossils. Another paleontologist, say working where I am in Virginia, might be excavating in a sandstone, and they might find the same trilobites, telling us that the trilobites could live or were deposited in different types of environments, some with sand, some with lime mud. And if you see the same fossils above them in both places, a little coiled ammonoid, or a fish fossil above that, if you see that same pattern in two places and the rocks are independent of one another, the pattern of fossils must be something real. You're finding it in multiple places, and this is what was determined in the early 1800s, that these patterns of fossils were consistent from one place to another. Sometimes there were slightly different fossils, but there was still enough consistency that you could work your way around and figure out where you were in this building column that they were making. So the geological column then was built on the basis of patterns of fossils that were found in stacked assemblages of rocks. The geological column was not built by evolution. The geological column was built before evolution was an idea. Now, it was built in tandem with the developing ideas of a very ancient Earth. And there are some assumptions that go into the geological column about two organisms that are found in the same layers, distant apart, must have lived at the same time. And they believe that the reason why there are different animals above and below them is because of extinctions. Now, I think, on the other hand, that these animals were living at the same time and they were being deposited during the flood, and that it's their ecologies and their ecosystems that are being deposited in some sequential fashion. So it's not subsequent extinctions and recreations of new things by God. That's kind of what people were thinking in the early 1800s, as God was continuously making new things and letting other things die out. I think that this was part of a singular cataclysm, at least until we get to the post-flood world. Then we might have some different processes going on. But nonetheless, Darwin proposed evolution as an explanation for this pattern, not inventing the pattern himself. And that's something that in creation literature has sometimes been confused. So, which layers of rock, then, if we can establish that the geological column is a basic reality, that we can do this consistently, and I can say from my own work in paleontology, yeah, we can follow this on a nice resolution up and down the column. So where are the human fossils found? Well, they're found in the very top of your handout, up over here in what's called the Pleistocene and the Holocene. There's one or maybe two uncertain records of Homo in the Pliocene, but it's all way up towards the top. Conventionally dated, this would be the last 2 million years-ish or so for the various specimens of Homo, as deep as maybe 2.5 million years, which is just below this dividing line between the Pleistocene and the Pliocene. So this is all stuff that's on the very top of the column itself. So that one. Are they flood or post-flood? Okay, that is a trickier question. How far up through the column does the flood occur? Does the flood explain all of our fossils or only a subset of our fossils? And if a subset, is it a big subset or a small subset or what? So flood or post-flood? Most of the localities that we have human fossils, members of the genus Homo or similar types of things, are discovered in two categories. One is that they are in very near-surface gravel deposits that are, or ash deposits or riverbank deposits, things like that, that are on the top of the topography, very similar to the topography that we already have. So they seem to be following more or less the local geography. And these are isolated and localized deposits. They are not ones that we can trace very easily from one area to another. It might be only in this valley versus the next valley over, as opposed to the rocks underneath, which are folded, and so you can follow the same underlying flood rocks because they've been bent and tilted and folded and they cut across the whole area. But instead, no, these hominids are found here in this group right over here, but they're not found in the sediments over here in this valley, which look a little different because there's a couple of different rocks here compared to the ones there. So that's one set, and a lot of the stuff in Africa historically, for example, has been in these localized ash deposits and riverbank and lake deposits. There's been quite a bit more that fall now into the second category in Africa, and especially in Europe, of things that are formed in caves. You know, when we think of Neanderthal fossils, we think of them as cavemen, in part because some of the very first fossils were found in caves, like the cave that Todd was mentioning the other day, where we have an individual who was buried, whose grave was excavated, they were dug out, laid down, and then put back inside. That was in a cave in France. So, in that case, then, both of these are very localized. Caves are small location. Sometimes they can get big, but they are localized sorts of things. They don't have the widespread distribution that we see with rocks that we typically believe to be part of the flood. So I'm going to focus here on caves and get us an idea of what it means then for how we approach the question of flood versus post-flood, because maybe this was a cave that was formed during the flood, and people ran into the cave and then they were killed. Is that a possibility, or is this a cave that had to exist in the post-flood world or something like that? So a couple of pictures here, one of an actual cave and one of a schematic coming from our textbook that I was privileged to write along with a couple of their colleagues called The Heavens and the Earth. And the majority of caves are made inside of the sedimentary rock of limestone. There's not a small number of caves to be found in and around this area of the world. Your patch of the country has got a lot of caves. Where I live in Virginia, I'm sitting on metamorphic rocks, and we don't have limestones. We have other sorts of rocks, and we have no caves. But if I hop over the mountains from where I am and I get into the Shenandoah Valley, there's a whole lot of caves up and down the Shenandoah Valley because the valley is made of limestone. So what makes limestone the sort of thing where caves form a lot? Well, it's because of the mineral that limestone is composed of. Sorry, again, my English. Of which limestone is composed. And that is the mineral calcite. Calcite is made of carbon, calcium, and oxygen. And it is a chemically very unstable material because it will react with acids, and the acids will dissolve it. And so a good example of this is Alka-Seltzer. Some of you are old enough to remember the jingle, plop, plop, fizz, fizz, oh, what a relief it is. Alka-Seltzer to the rescue of us geologists, because it means I can always do a demonstration in my class. Oh, I would carry little tablets of these things to my class and like, all right, we're going to watch a chemical experiment. I plop an Alka-Seltzer and it starts to fizz. Why does that happen? Well, it's because Alka-Seltzer has citric acid crystals in a matrix of calcium carbonate, of calcite, that's been ground up from shells or limestone or other sorts of things. And when the citric acid hits the water, it instantly dissolves, and then the water becomes acidic and attacks the calcite, and you end up with all these bubbles. It's carbon dioxide that's being released as the solution process is happening. And the citric acid gives it a passable flavor of diet Sprite. It's not too bad as far as medicines go. So the same thing basically happens with caves. When caves are subjected to acidic waters or acidic liquids, they dissolve. And they can also reprecipitate. And so stalactites and stalagmites are forming in caves because limestone has been dissolved somewhere. The water is carrying these materials and eventually redeposits them as the drips come down. And so you can dissolve, and then you can reprecipitate, and you can move this stuff around. So our cave systems are built into existing rocks. So the rock must be made, then the rock must be dissolved. In order to get things inside the rock, then you have to have a sequence in which somehow there is access from the surface down into the cave system, either because the rocks have been lifted up to allow the caves now to be exposed, or they've been eroded down and now there's holes that drop you down into the caves. And we see examples of all of these around the world. So calcite, as I said, it's made of calcium carbonate. It dissolves. I saw that slide ahead of you guys. Sorry about that. There's the Alka-Seltzer. I had the presenter view, and I was like, oh, I've got picture in picture, and I didn't. But there's the picture of it, a picture of calcite, a particularly nice specimen of optical calcite. Calcite will do this cool thing where it'll split an image as light passes through it, and we can use that. I actually use that to calibrate high-sensitive lasers. They'll use very, very pure calcite for that. That stuff costs hundreds of dollars for a small piece. In our geology kits, we don't put those in there because we want people to actually buy them and not just look and say, oh, that's cool. As a result, then, it seems best to understand caves as post-flood systems. They are rocks that form underwater in oceanic conditions for the most part. There are some freshwater limestones, but they're rather different than the stuff that we see around here. You're going to find lots of fossil shells around here of marine organisms, corals, brachiozoans, brachiopods, clams, nautiloids, etc. And those are oceanic organisms. Then this rock has got to, this mud of lime has got to solidify into rock. Then later it's got to be lifted high enough or put in some sort of position where acids can attack it and create the caves. And then it's got to be lifted up so that those caves become exposed and people can go into them. It seems very unlikely that all of that is happening within the flood so that people are still around and running away from the flood and running then into caves. But there's another factor that helps us to understand that the caves are probably post-flood, and that is the deposition of the muds and the sediments inside the caves themselves. Because not only are the caves dissolved, but then they have their own kind of sedimentary system inside. So one of the caves out there, Dr. Wood mentioned this one yesterday in the context of the Hobbit people, the Lingua cave in Flores, Indonesia. Here is a picture of the cave and the excavation site. Here is a photograph of the Lingua skull, LB1, and it's a very small person. The skull is this big. It's very, very tiny. The whole person stood 3 foot 4 inches tall and was a 30-year-old female on the basis of what we can see from the growth of the bones and the eruption of the molars and the wear of the molars. So they had their wisdom teeth in and were using them. This is a person who was full adult and was as large as when my daughter was 5 years old. And weighed about the same, about 50, 60 pounds. That's really small, really small. I don't know if they had fuzzy feet. So that's the discovery of Homo floresiensis. It is in a cave system that is made of limestone in that area, and it was colonized after the flood because we can see the sediments in here are completely different from all the sediments outside. The cave has its own system. And the sediments in here don't look like a big washover. They don't look like coarse material and gravels or things like that, lots of mud coming in from outside and burying things in the cave. It seems like the cave has got its own sediments and drips and mud. World. Flood is responsible for bringing people into that. That's not what I would expect to be the case. So again, we've got people in there that are very, very tiny, very small, only a few feet. Another example of this is the cave system in South Africa, the Rising Star Cave System, home of the deposits of Homo naledi, a very new taxon that was first discovered in the mid-20-teens, 2015, I think, for Homo naledi. And this is a big cave complex. And now they have found not just the first initial pit way back down here in what was called the Dinalidi Chamber. This was originally found by a couple of cavers who were working their way through the cave. And this is completely dark. Can't see anything. You need to bring lights down in here. They went all the way through. They squeezed through this. They call this the Superman crawl because you have to put one hand forward and you have to scooch your way like that to get through. It's as narrow as they got into this big chamber and over this thing called the Dragon's Back, and then they went down this chute, and when the cavers got this far, they found that they were standing in a room full of bones, and they went, no, 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 not us, not here. We know about these movies, and we're not going to be part of it. So they left, and they went to the university. They said, there's bones in a cave, your deal. Not doing it. And so there's a big discovery of loads of bones over here. These are the bones that were recovered simply by surface collecting. They didn't even start digging. Just collected bones on the surface of what is now known as Homo naledi. The lead researcher even had to get small females to do this because guys were too big. So he actually had to put out a call for new graduate students that were slender women. And it's like, I read his post, it's just kind of amusing. So lots of different specimens here, and this is deep, deep inside the cave. And again, the sedimentation is different in different parts of the cave, and this doesn't look like some sort of wash in. It looks like water does occur in the cave. Water level rises and falls as groundwater rises and falls inside the cave, but it's not wash-in material. So because of that, it seems that all of the fossils are found in the Pleistocene, and it seems, which is also coincident with the Ice Age. So when we think about the Ice Age and we're thinking about Homo fossils, this is pretty much all part and parcel together. So then geography. Where are the humans found? So we now know our answers to these questions, but which locations? I've given you a couple, and what was world geography at the time? Were the continents in different places or anything like that during the Pleistocene? Well, basically no. During the Pleistocene, the continents are more or less in the same position. They scooch a few miles or so, and so a slight difference, but not very much. And during the Ice Age, or during the Pleistocene here, where are the people? Well, we see things like Homo erectus, which Todd talked about yesterday, in Africa, also referred to there as Homo ergaster. Homo erectus is out over here in places like the Republic of Georgia and out into China and Indonesia. The original Homo erectus fossil was Java man, so island of Java out in Indonesia. So that's one of the first members of Homo that we see. After that, we see, for example, Homo naledi in South Africa. We see the Neanderthals and the Denisovans and Homo floresiensis in places like Eurasia and Flores, Indonesia. And the first time that we see fossils of Homo sapiens, our own particular morphology, they show up in Africa before moving around to other parts of the world. So we don't find human fossils everywhere in the Pleistocene. We find them in the Old World. Okay, this is primarily even, it's not until we see some Homo sapiens in Africa and out over here before they eventually even make it to places like Australia and eventually the Americas. That happens later on in the story. What was world geography? As I said, it was basically the same, but it was icier. This is a picture of what things would have looked like from space. Glacial max, so at the farthest extent of glaciers, we would see that the Earth has got a lot of ice, but not all ice. This is not a slush ball. The Earth is not a giant snowball. We tend to think sometimes about the Ice Age that it was cold everywhere and there were glaciers everywhere. No. If you were living in equatorial Brazil, it was hot and humid. It was tropical. It was very warm, and you did not know that there was an Ice Age going on because it was simply dang hot all the time. There's still a lot of mosquitoes around. They didn't die during the Ice Age. But if you were living in Europe, you would have had to shift your colonies further to the south as the glaciers continued to advance from the north to the south, and they expanded in the Alps outward. So we see extensive mountain glaciation. You can see the Andes, for example, very extensive glaciation. The Himalayas have big, big glaciers all over them. But if you look at the top of the world, if you look from the North Pole down, you can see that the glaciers are basically like a circle. And if we took a look at Antarctica, right, it's basically a circle because there's only so many places in the world where the temperature is so cold that you can sustain glacial development. And sooner or later, the glaciers get to places that are warm enough and they melt. I'm going to skip through a couple of slides because we don't have a whole lot of time to go through the mechanisms of glaciation. But the Ice Age is a post-flood event. And that is something that creationists have thought about for quite some time, that it is specifically well manifested in places like North America, Greenland, Northern Europe and Asia, and in Antarctica. And today, there are still major ice sheets over Greenland and Antarctica. So from a geological perspective, we are still in the Ice Age. We are in a glacial period. Geologists would define an Ice Age as a point in time when there is solid ice over continental regions on the Earth. And we would be in what we would call an interglacial period, where the glaciers have pulled back substantially. We don't have them everywhere. We do have them in a couple of places. And this is supposed to have happened in pulses during the Ice Age. It wasn't just one big monolithic move. There were some back and forth that happened on this. So I'm going to skip through how the Ice Age happened in the interest of time here. It's fun stuff, but not necessary for us at the moment. The big takeaway then is then with this world geography, how are people then getting around? Well, one of the things that's pretty cool is that, literally because it's the Ice Age, some of these I come up with right on the fly, and we'll see what happens next time. So what happens when you store lots of ice on the continents in the form of glaciers, that water had to come from somewhere. And that water comes from the oceans. So the evaporating water from the oceans rains down as snow and comes down as more snow than can melt, and so the glacier builds and builds and builds and builds and builds. And as a result, the water's not getting back to the ocean very quickly, so ocean levels drop and drop and drop and drop. And as a result, the geography of the Earth, even though the continents are in the same places, looks radically different. Can you see Indonesia here on the screen? This is a massive expansion of Asia. This is all walkable land. You can't do that today because when the glaciers melt, where does the water go? Back to the oceans. And sea levels rise and cut off areas that were once before passable. The difference between then and now in terms of the elevation of the ocean, vertical elevation of the ocean, is over 400 feet. 400 feet between glacial maximum and now. So I live in Virginia. If I want to go to the beach, if I want to go to Virginia Beach, I have to drive about 4 hours. I would have to probably drive another 4 hours, or at least 3 if I had a good highway, to get to the beach during glacial maximum. It would be a long way out. The North American shelf is big, and Florida is this enormous thing that just about touches the Caribbean islands. Not quite, but to the point where you could probably see them from where you were. The Yucatan Peninsula is gargantuan and almost touches Cuba. And then there's another one over here, and we don't see that because now that's all covered over. So this allows, in the late 80s, to actually get to the Americas by walking, because they can now connect themselves across the Bering Strait. Here it is, you can see a little bit better. You can walk from Asia over to North America and never know that you left a continent, because the connection point between the two of them is hundreds of kilometers across. We call it Beringia, after the Bering Strait. And even today, there are parts of the Bering Strait that are only about 30 feet below, above sea level, with a 30-foot depth to the sea. So it's close, but it's all closed off now, and you can only do it by boat. You still could never quite get to Flores Island. As Dr. Wood mentioned yesterday, the Flores hobbits had to get there by boat. That was never connected. You could never get to Australia by walking. You had to get there by boat somehow. So there are a couple of these places that are still isolated from the rest of the world. So we had Beringia This gives us an understanding of where some of our Ice Age fauna comes from. Our mammoths and mastodons came from Asia. We call them, for example, we have the North American bison. It's not North American. It was only North American when the Europeans got here. But it was an Asiatic bison that migrated over here into the Americas, and then after the Bering Strait was closed, the bison couldn't get back, and neither could the people. They could kind of travel. They did have some boats and things like that eventually. But we now had a group of organisms that are locked in the Americas, and they can't get back. And the Europeans find them for the first time, go, oh, wow, it's the American bison. And as a paleontologist, I kind of snicker and say, this got here barely before you did. But we've got bison, we've got mammoths, we've got mastodons, we've got predators, and humans follow them. They're following the herds as they go from one place to another. And so that's how eventually we end up with what are called Native Americans, because they're actually Mongolians, more or less. They are northeastern Asians who came to North America. And that makes perfect sense as we've been able to now study genetics and determine kind of people's pathways. Like, oh yeah, sure enough, that's confirming the model that we had about their migration from before. And so what we find here is that there's some interesting things when we think about ourselves as Homo sapiens, not some of the other fossil hominids, but we think about this. Homo sapiens, as I mentioned, that physical form shows up in Africa after Homo erectus, after Neanderthals and whatnot. And even as a creationist, that's the order that we find if we can trace the rocks properly from one place to another. From there, they leave Africa and they meet up with another group of people, Neanderthals. And when people meet with people, if they don't eradicate one another, they tend to marry one another. And as a result, members of Homo sapiens started intermarrying, interbreeding, having kids with Neanderthals, and having kids that were hybrids between the two of them. It's people meeting people and having kids. All of these are descendants of Noah's family, but they're descendants of Noah's family that have been isolated from one another, look different from one another, but find each other, and it looks like they got along well enough. And then as Homo sapiens continues their expansion, they take those genes that they picked up from the Neanderthals, and they bring them to other places. They bring them to Asia. They bring them up over to Australia and over to North America and South America and to Europe. But there wasn't very much flow of Neanderthals back into Africa. So if your heritage is from sub-Saharan Africa, there's very, very, very little Neanderthal DNA that's mostly coming from backfill from other people that had met the Neanderthals and their kids eventually coming back into Africa, but not the Neanderthals themselves. And so we can see that everybody in the world that is not sub-Saharan Africa, African by descent, carries somewhere about 1% to 2% Neanderthal DNA with us. I do, for example. And if you're from sub-Saharan Africa, you might have a small fraction of 1% that has gotten its way back in. But that was a very fascinating find about the distribution of Neanderthal genes in the modern human population. So the Ice Age ends, but the massive glaciers persist, as I mentioned, in Greenland and Antarctica. We're still in this kind of glacial, interglacial period. Global temperatures are cooler in the than they were in the pre-flood world, or even in the early post-flood world. The warmer, wetter. There's a lot more places where there was high precipitation rates that helped to create the glaciers, but over time the glaciers start reflecting a lot more light back out to space and start cooling the Earth down by reflection and whatnot. The climate then is much more stable now than it was in the early post-flood period. It's not to say that the climate is stable. It's not to say that the climate's not changing one direction or another. It hasn't continued to change throughout history. But it's far more stable now than it probably was in the early centuries after the flood, which were radical enough that they raised sea levels hundreds of feet up and down. And thankfully, we're not seeing that every other day. Otherwise, we'd be all living more towards the hilly parts of the world. And in fact, if you melted all of the glaciers in Antarctica and Greenland right now, it wouldn't flood the world. If you ever saw that old Kevin Costner film, Waterworld, my apologies, I'm sorry, that was a rough one. That was not good. But yeah, the idea was the glaciers melt and all the world is covered with water and there's only a few bits of land left. And no, that wouldn't happen. We'd lose pretty much all of the East Coast right along the edge. We'd lose all of Florida. And Washington, D.C. would be underwater, but it already is, so that doesn't matter too much. I'm living in Lynchburg. I'm 700 feet above sea level. I'd be fine. Beachfront property would now be an hour drive instead of 3. So, you know, Farmville, their property values would be way up. But the world wouldn't be completely covered with water. But now we've got some answers. Now we've got an idea as to what's going on. The deposits that we find our hominids in are localized, small regions that have particular geological features of being in place and not being long-distance sort of things. We see evidences of graves and burials. It doesn't seem that if people are trying to survive the flood because wave after wave is coming after them, that they really have time to bury Uncle Art in the cave. You need to establish stability in your society, and there's no stability during the flood. Everyone's going to die. So based on these, I think we've got a very good handle from a biblical creation perspective of how to orient ourselves with respect to the human fossil record. So with that, hopefully it'll make sense of some other things that Dr. Wood's going to be talking about as he introduces us to cavemen in the Holy Land, and we get an idea of what's going on well before Jesus and before Abraham in the post-flood period as to what's happening there. So thank you very much for that. I look forward to seeing you again this afternoon.
Thank you, Dr. Ross. Again, if you have questions for any of our speakers, please do be developing those and writing them down or sending them to the phone number, which I believe is in your handout. Oh, there it is. Look at that. Just speak the word, and there it shows. We have a short break now, about 5 minutes. There is coffee. There are still some refreshments in the foyer area, so please help yourself to that. And in about 5 minutes, we're going to begin with our next speaker. Thank you.